bit about me. My name is Bhavna Soman. I'm a security researcher with the Windows Defender research team. In the past, I used to work in threat intelligence and doing APD response. In my day job right now, I work on classifying malware in real time, building models for that. So this project kind of came about as an amalgamation of my past doing threat intelligence and what I do right now with machine learning. So when most of us hear threat intelligence, we think of the automated IOC feeds. But there is a much richer data set that describes the actions of threat actors, their tools, tactics, procedures, victims, etc. And much of this data is unstructured. It's contained in blogs, white papers, incident response reports that people have to read and analyze. And that's kind of the bulk of the work that a TI analyst has to do. Let me show you an example of the kind of workflow they follow. So maybe you're an analyst who works for an org that's concerned about attacks from an Eastern European country. So you go out and start to do some reading. Maybe you learn about these three attackers, APT 28 and 29, which have been active since 2007 and 8, and then Dragonfly, which is kind of newer, circa 2011. And you read up about their tools, tactics, and procedures. Dragonfly is focused more on cyber espionage. 28 and 29 have more political targets, with 28 focusing more on Eastern European governments, and then 29 more on Western political institutions. So you read up all of this information about them, and then maybe you create like this shoebox of TTPs, which is, okay, so this particular APT uses spear phishing, and then they drop obfuscated PowerShell to get to put their malware implant, so on and so forth. But this data is not really, it's very complex. It's not useful yet. So if you're a really good TI analyst, you create a graph like this, connecting the TTPs between these actors. And now you can start to make a little bit more sense. You can clearly see at a glance which TTPs are common between these three. In fact, you can see that there's not that much that is common between them. In fact, APT 28 has a very complicated networking infrastructure, which is mostly absent from the other two. Maybe you go a step further, and then you overlay this data with the prevalence of each technique. So now the size of the bubble is dependent on how prevalent each technique is in general, not just with these attackers. So now you can start to use this graph to maybe drive some data-based conclusions for your organization. Maybe you can recommend that you focus your network defenses or choke points on detecting obfuscated PowerShell or credential dumping tools, because you can show clearly that those are the techniques that will effectively help disrupt the tool chain of the attackers that you're concerned about. And then you might recommend that, hey, let's not focus so much on time stomping and bootkits, which, they're really cool, but in terms of your, return on investment, they will mean less for your organization. So this is the kind of manual work that TI analysts do. And what we're going to try and think about is, what if this was as automated and as easy as IOC feeds are today? So can we do this with machine learning? That was the question I was trying to answer. If we could, our input would be all of this written material, blogs, white papers, maybe past incident response reports from your org. And then there'd be this black box of machine learning, which can extract the actor names, the tool names, the techniques that they're using, and extract the relationships between them. And then the output would be the type of graphs that we've seen. So we're going to focus on building this black box. For the rest of the talk, this is my agenda. I will introduce the concept of named entity extraction. I will talk about how you can use a machine learning / deep learning way to build your own cyber entity extractor using open source data. The training data, what kind of feature extraction we used, the models that worked for us, and then successes and failures. I will give you a short demo of the tool that we've built, and I'll wrap it up by how this can help drive impact. All right, what's named entity extraction? This is an article that appeared in the Times of Israel a while back. If I pop the text from this article into any off-the-shelf text analytics toolkit, like the ones provided by Azure or Google, I can very easily extract the entities that this text is talking about. For example, this is what the output would look like. Israel and America and, are geopolitical entities. Static and Ben El-Tavori are people. And even though static doesn't sound like the name of a person, the algorithm is intelligent enough that based on the context in which it appears, it can extract that and identify that correctly as the name of a person. But when I apply these toolkits on an APT report, they completely fail. So for example, if I have this type of text, and if I pop this into like an off-the-shelf text analytics toolkit, it does not extract any entities. The output that I would expect looks something like this, like dropping elephant China strats and patchwork, they're the actors, and spearfishing and watering hole are the techniques. And I want them to extract this, and they kind of don't do that right now, so we decided to build our own. Let's talk about how we can get the training data for building the cyber entity extractor. For our training data, we used APT Notes, which is a publicly available GitHub repository that's maintained by security researchers. It has links to white papers going back way in the past, and it also has tools to download them, etc. So we used that, and we used publicly available TI blogs that were collected by our team since June 2018. In all, we got about 2,700 documents. And at the top graph, you can see the distribution of tokens within our documents. You can see that on average, each document had about 2,000 tokens. And on the tail end, there are some documents that had upwards of 70,000, 80,000 tokens. On average, most of these tokens belong to the outside class. That is, they were neither a malware name nor a technique phrase or anything like that. The lower graph shows us the distribution of the terms that we care about within these documents. So you can see that it's very low for malware tokens, actor tokens, and technique tokens. So this tells us two things. One, that our data set is very small. We have only 2,700 documents. And second, that we have a massive class imbalance. So if we were to train a classifier, we'd have to take that into account. Also, we'd have to guard against overfitting. And from past experience, we know that deep learning algorithms don't tend to work as well with such a small data set. So we'll try some traditional machine learning methods in addition to the more sophisticated deep learning ones. To label our training data, we relied on the Carrot dataset, which is provided by MITRE. MITRE is an American nonprofit. It kind of just contains a JSON structure with the list of all the actor names, their aliases, and the techniques they use. And I just put in a screenshot of that there. We used the data as a list of tags, and then we annotated our corpus using longest extent pattern matching. The thing to note about MITRE is that it's kind of out of date, that it's not under active maintenance. So there are a lot of actors that have come up in recent times that are present in our data set, but which are not present in the MITRE data set. So they kind of got tagged incorrectly, which makes our training data very noisy. But since that is the best we can do short of manual annotation, that's what we went with. And we'll keep this in mind when we do our evaluations for models. This is how we did the tagging. We use the IOB style, which is inside, outside, beginning. It's very common in natural language processing-based tasks. So here you can see that Ben El-Tavori is a whole phrase that indicates one person. So the first token in that phrase will be tagged with a B-token tag, and all the subsequent tokens in that phrase will be tagged with I-person, and so on. I meaning inside and B indicating beginning. So if we have like a similar text blob from our domain where we're talking about numbered panda, this is just, I think this is from Wikipedia. This is how that would get tagged, so numbered panda is a phrase that indicates a bad actor. So the first token in that phrase will be B-bad actor, and the panda will be I-bad actor, and so on. All right, let's talk about feature extraction. For our feature extraction, we broadly used two types of features. We used the traditional features, which are common for natural language tasks, such as word type, part of speech, lemma, etc. And then we used word embeddings. In very simple terms, word embeddings are vector representations of words such that the semantic or the contextual meaning of the word is captured by the numeric vector that is extracted. So that would mean something like, for example, if two words have very similar meaning, or if they appear in the same context a lot, then we would expect that the cosine similarity of their word vectors would be very high. And we extracted our word embeddings using word2vec with 100 dimensions. This is just a screenshot of generic word embeddings. I kind of wanted to give you the idea of what they mean. And here we can see that words that appear in a similar context get clustered together. And what we want is that since our word embeddings were trained on a cyber domain specific data, we would want the words that cluster together would be that they cluster based on their meaning in which they're used in that context. So this is a visualization of our word embeddings visualized in TensorBoard. And since our domains, since these are trained on cyber data, we see that that kind of meaning is encapsulated in the points that cluster together. Here we can see that the points closest to APT28, two of the points closest are just aliases of it, Sophie and TG4127, and then two others are related to it by attribution. Here's another example. When we look at the words closest to dog call, we see that the closest words are Purim, shutter speed, and are you happy? And all of these names are the names of malware that are used by one particular APT, APT37. When we visualized all the vectors together, we can see that the green and blue tokens, which indicate actor names and malware names, are clustered on one side, whereas the tokens which occur in techniques are clustered separately. All right, let's talk about the architecture. We had a very simple architecture. We used the blogs and the white papers that I talked about, and we used HTML and PDF parsers to extract the text. Then we put them through some very simple text pre-processing, just removal of unprintable characters. And then we extracted the word embeddings, as I described. We split our data corpus into two, 80-20 for the training and test set. We extracted the traditional features that I talked about earlier, combined them with the word embeddings, and this is the training data that we use to train our model and then test it. The first model that we tried out is conditional random fields, or CRFs. This is a statistical modeling method. It's not deep learning. It's pretty close to hidden Markov models. You can kind of, in a simple way, think of it as logistic regression for sequence labeling problems. It's in fact commonly used in natural language processing tasks, biological sequencing, and even computer vision. We can say that it has short-term memory, and let me explain a little bit about what that means. We have the matrix you see on the screen is a transition weights matrix, and it shows the transition weights between the various classes. So you can see that the likelihood of transition from an O class to a B bad actor class is positive. But when you see the likelihood of the transition from an O class to an I bad actor class directly, you see that it's a very low number. And that makes sense, because in a sentence, you might have an O term, but you'd have a B bad actor term, and then you'd have an I term. That is why the likelihood of going straight from an O to an inside phrase is very, very low. And that makes sense. And this is what we mean by when we say CRFs have short-term memory. That is, the probability of a particular class occurring is dependent on the classes that are occurring around it. And in our experiment, we tried two versions of the CRF, one with embeddings and one without embeddings, just with the traditional features. And that was because we kind of wanted to illustrate, we wanted to make sure that the word embeddings were adding value to the model. We also tried a model based on LSTM. And LSTM is a special type of recurrent neural network. In our architecture, we had two stacked bidirectional LSTM layers with dropout. For our loss function, we used categorical cross-entropy, and we used softmax activation for the final layer. The problem that we're trying to solve is called domain-specific custom entity extraction. And this type of architecture is quite typical for that problem based on the available literature. The only thing that we added sort of is adding the dropout layers, and that's because, like I'd mentioned earlier, since we have a really small data set, we're at risk of overfitting, so we added the dropout layers to improve the generalization of the model. All right, let's come to the assessments. First, I wanted to share with you the recall counts to give you an idea of how many entities of each type were to be extracted in our data set. And you can see off the bat that there were very few technique entities, and that's a limitation of our training data set. The yellow bars are the LSTM. The blue ones are CRF without embeddings, and the red ones are the CRF with embeddings. We can see that for the actor class, the LSTM does much, much better than the others. But in all the other classes, their performance is pretty similar, where the trade-offs could involve just efficiency. Here we see the recall and precision. And we have the positive precision and positive recall here because we have class imbalance, so that's why. We can see that the precision for all the algorithms, particularly the CRFs, is really, really high. But in terms of recall, we see that the LSTM quite clearly outperforms the CRFs. This is great, but we want to test the performance of our models on unseen tokens. What we want to know is, if the algorithm sees a new actor name that it has not encountered before, will it be able to find that? To determine their fitness for that particular use case, we judge their performance on just the unseen tokens. And here we can see a very, very different picture. We can see that there is a huge performance drop in both the LSTM and the CRF without embeddings, whereas the CRF with embeddings, it has perfect precision, and it is the only one that has any sort of recall on the unseen tokens. And that's very important for us, which is why this will be the model that I showed you in our demo. All right, it's demo time. So this is just a toy web application that was created. I'll be entering text into the text box, blobs of text from other white papers and stuff, and we'll see when I run the model on it, the entities get extracted. All right. So here we can see that PawnStorm, which is also, I think, an alias for APT28, the algorithm could correctly identified all instances of the actor as well as the techniques that it's using. Now let's try some other text. The text that I'm going to put here is the various blobs are not related, but I just wanted to illustrate the different types of entities that our model can find. And here again, we can see that it correctly finds the actor, which is Scarlet Mimic, and the techniques that it's using, which is spear phishing and watering hole, etc. And the second paragraph is about a different piece of malware, Havextrat. And again, in that blob, it identifies correctly the malware families, etc. I wanted to give one more example about how this model is not just doing pattern matching or text recognition. It is extracting and identifying these entities based on the context in which they appear. So if I just type a dummy sentence, basically this is Fancy Bear, and we know that Fancy Bear is the name of a common, is the name of an actor. And if I run the model on it, it doesn't say that there is any actor present, and that is as it should be, because this sentence does not look like it's talking about an actor. It's probably talking about a teddy bear. But then if I put in another sentence where the context is more clear, where Fancy Bear is used in the context of an attacker, and then we run the model on it, we'll see that the model is able to identify the actor. Yeah, so this is the really key piece here. The algorithm is able to identify the actor based on the context in which they appear, and it's not just doing pattern matching. Cool. So this is just V1. We have a lot of work to do. We want to try attention networks, which is apparently the latest and greatest thing in natural language processing. I mentioned that our data set is quite small, so we want to explore data augmentation using generative methods. We want to do more sophisticated relationship extraction. Right now, we're doing it with just very naive co-occurrence, and also work on extracting temporal relationships. I want to close it by talking about the impact that this type of automation can have. In the beginning, I showed you this slide where our imaginary threat analyst kind of helped their organization decide where to focus some of their detections. We created a similar graph from the data set that we got. We extracted automatically all the TTPs used by a commodity malware family, Emoted, and a spate of other APT actors. There's some pandas and snakes and stuff in there. But here, clearly, you can see the overlap between the techniques that commodity malware use today and that APTs use. We can see that obfuscated PowerShell, process hollowing, scripting, these are all techniques that we think are complicated, but they're used by commodity malware. So this type of automated insight can be used can make the job of a TI analyst much easier and can help them drive their organization to put detections and choke points in these places so that they can not only detect and suppress the annoying commodity malware, but also the high-profile APT attacks. In conclusion, I hope I've convinced you that it's time for threat intelligence to move beyond IOC feeds. There is a rich, unstructured data set that can be extracted with machine learning, and we can make the graphs and the timelines that we saw with that. And we can use this data to make better decisions for the security of our orgs. That's all I have for you. Thank you.